In this module, we're going to talk about probability functions. What I want to do is just quickly touch on what I think the important points are to help you when you go back and refresh your memory from courses that you've taken before. So remember that we have two kinds of random variables. We have discrete and we have continuous. But let's start with the discrete case first. And remember, the idea of a discrete random variable is that it takes on discrete values. And so, for example, if my discrete random variable x happened to be a count of Hondas in the parking lot, then I might have 0, 1, 2, 3, and so on. And I might have come up with an idea of the relative frequency of occurrence by maybe taking a lot of observations over time of the cars in the parking lot beside Mitchell Hall. And so what I might find out is that if I have probability on the vertical axis, I have, say, a 10% probability that there's just one, and maybe in fact, let me use a different color here. I might have a 10% probability that there's just one, and maybe a 5% probability that there's none. And what I might find is that this probability function takes on some sort of profile like that. Okay? And so this is the probability that xi equals 4. Okay? This is, if that's 5 and 6, the probability that xi equals 6, and so on. And so the notation that I'll typically use will be to have as a subscript the random variable that I'm talking about, just to remind ourselves. And then this is lowercase because this is talking about a specific outcome. And here what we're doing is we're saying this is the value of the outcome. Okay. So this is what the probability function would look like in the case of a discrete random variable. What I would have is some sort of a function px of x. And sometimes we have a closed form analytical expression for it. But other times, that function essentially might be described by a table of probabilities for different values. So you'll run into both situations. So that's what the probability function looks like for a discrete random variable. And one of the things that I could do if I wanted is talk about a cumulative probability function. And this might be, let me give it a capital F. And so what f of this would be the probability that this random variable is less than or equal to k. And how do I get that? Well, what I do is I take that function and I just add up for all the values up to k, and in this particular case. Okay? So the idea of a cumulative probability function is that we are talking about the cumulative probability of being less than a certain value. And so what we do is we start to add up those values progressively. Let's go back now to the continuous variable case. So if we're talking about continuous random variables, remember that we talked about the continuous probability density function. So we have a probability density function. And we're going to call it fx of x like this. Okay. Now, if I talk about, say, fx of 3, that's the probability that x is in an infinitesimal neighborhood of 3 plus a small amount and 3 minus a small amount. So one of the tricks with continuous random variables is that the density function, which is the continuous equivalent of the discrete probability function, its values, if I talk about fx of 3, it talks about the probability of being in a small infinitesimal neighborhood of 3. Why is that? Well, the reason is that for continuous random variables, the probability that a continuous random variable is equal to exactly 3 is 0. And the reason for that is that if the probability that a continuous random variable equals 3 was non-zero, well, because we're talking about continuous random variables that take on values on the real line, to start with, there are an infinite number of rational values on the real line, and there's not even a countable number of values on the irrational part of the real line. And so what it means is that if you started attaching probabilities to specific numerical outcomes instead of small little intervals, there's no way that you could attach probabilities to all of those and have all the probabilities add up to 1, which is what they have to do, right? Because the probability of something happening has to be 1. So probabilities always have to add up to 1. So that's the quirk with continuous random variables, is that when you see a density function, the probability or the value of that density function evaluated at a specific number is the probability that the random variable is in this infinitesimal neighborhood around the value 3. Okay? What's a very common probability density function that we have for continuous random variables? Well, probably the most common of the bunch is the normal distribution, right? The bell-shaped curve. And so there's the density function for a normal random variable. Remember that the center of gravity of that distribution is the mean. And then we have some sort of measure of dispersion or width of that distribution, and that's what we call the variance. Okay? So as we had in the case of the discrete random variable, we can also have a cumulative probability distribution function for a continuous random variable. And so what does that look like? Well, the cumulative probability distribution as we found before, where you had a sum, in the continuous case, you'll have an integral. And so the probability that x is less than a certain kind of value k is equal to the integral from minus infinity to k of fx of x dx. Note, there is no x multiplying that f, because we're not talking about expected values. What we're doing is we're saying, if I want to know the probability of being to the left of k, i.e. being less than k, then what I need to do is I need to add up all the probabilities. And what that means really is, what I'm doing is I'm adding up the area under the curve to the left of the value k. And so that's the cumulative probability distribution function for a continuous random variable. The form or the expression for the probability density function for a normal random variable is 1 over root 2 pi sigma. There we go. I didn't do such a neat job of writing that out. I'm sorry about that. But the critical pieces on this are that at the core of that probability density function is the square distance of the value x from that reference point, which is the mean. And you can see also that we've got the standard deviation, which is the square root of the variance in there that's providing some scaling. So that's the probability density function for a normal random variable. And it's one of the ones that we'll use most often.